In the last lecture, we talked about the test for goodness of fit, and that was a chi-square test. Today, we're going to talk about another type of chi-square test, the test for independence. So let's take a look at the situation here. In a study of high school students at least 16 years of age, researchers obtained survey results summarized in the following table. Now, this is going to be a chi-square test because the numbers here represents counts. They're counting how many people are in certain categories. And the difference between today versus what we talked about last time is that we have two sets of categories here. We're actually asking people two things. We're asking, do you text and drive? Yes or no. And do you drink and drive? Yes or no. And what do these numbers mean? This 23, for instance, means there's 23 people who text and drive but don't drink and drive. This 10, there's 10 people who text and drive and also drink and drive. Horrible people. And the question we're asking here is texting related at all to drinking? In other words, is texting independent or not independent from drinking? And this is why this is called a test for independence. So let's start off with what the correct H0 and H1 for a test of independence should be. H0 is going to say that texting and drinking are independent. In other words, they have nothing to do with each other. H1 is going to say texting and drinking are not independent. In other words, they are related to each other. And just like the other one, the goodness of fit test, we're going to be comparing an observed counts with expected counts. The original table, these are my observed counts. And this new table is the expected counts. And what's different is how you calculate the expected counts for a test for independence. So to calculate the expected counts, I'm going to have to go back to my original table and find the row totals and the column totals. The row totals, the total of the first row, so 10 plus 23 is 33. The total for the second row, 4 plus 13 is 17. Those are my row totals. I also need my column totals. So 10 plus 4 is 14. That's the total for the first column. The total for the second column, 23 plus 13 is 36, I believe. And then I also need the total of everybody in the study. So the total of all the numbers, and what I mean all the numbers, I mean all of the original numbers. So 10, 23, 4, 13, so add those up. Ten plus 23 plus 4 plus 13 is 50. You could have also gotten 50 by adding the row totals, so 33 plus 17 is also 50, or the column totals. 14 plus 36 is also 50. Now, how do I find the expected numbers? So for my expected numbers, I want the same row totals. So I want the same row totals as the original, and I want the same column totals. And I want the same total. So I'm calling it total, but the actual name for that is the grand total. So it's just the total of everybody in the study. And I want to fill in this table so that, assuming that texting and drinking are independent, what should these numbers be, right? If indeed texting and drinking are independent. And to figure out, I need to go back to Unit 2 and talk about when we talked about the definition of independent. So recall, that two events, A and B, are independent if, and we had a math definition for this. So two events A and B are independent if P of A equals P of A given B. And all this is really saying is that adding on this given B part doesn't change the probability of A. So A, given knowledge that B happened, is the same thing as just regular A. So that's what it means for B to not have any relationship with A at all, or B doesn't affect A at all. In this case, let's write in what A means and what B means. We were talking about texting and drinking, so let's let A be texting and B be drinking. So what this really says is probability of texting, I'll just write text, equals probability of text given drink. And let's write down what the probabilities are on the left side and on the right side based on this table. Left side, probability of texting. The bottom is going to be everybody. Everybody. So we don't have numbers here, but we do know that everybody should be 50. The top, how many people text? Once again, I don't have numbers here, but I do know that the people with text are whatever's in this box and this box. And I know that that total is 33. On the right side, probability of text given drink. And remember, this is conditional probability. So this part, given drink, it's just telling me to focus on the drink numbers. For the top and the bottom. Focus just on the people who drink and drive, which would be this first column. Okay, so focusing just on this first column, what is the total? The total is going to be 14. And then focusing just on this first column, how many text? So focusing just on this first column, how many text? It would have been this box, this first box here, which there's no number there, so let me put a letter here. Let's call that X. That'll be there. And now let's solve for X. So to solve for X, I need to move this 14 over by multiplying it over to the right side. And I'll get 33 over 50 times 14. And then let me do that real quick. So 33 over 50 times 14. And I get 9.24. Let me actually write that in green. So what we just found was if texting and drinking are indeed independent, the number that goes here should be 9.24. Now, that was some algebra and that was a lot of calculations. Now, could we find these numbers without having to go through this algebra? And the answer is yes. So let's take a look at how we actually got to this answer, right? How do we get to this 9.24? We took 33, which was the total of the row. We times it by 14, which was the total of the column. And then we divided by 50, which was the total, or the grand total. And that's basically what you do. So let me write that down as our formula. To get the expected, instead of going through this algebra part, we can just do row total times the column total, and then divide by the grand total. Okay, grand total is the correct term, but I'm going to apologize. I'm probably going to just say total. Okay, so let's see how we fill in one of these other boxes. Let's fill in the bottom right box. To fill in that bottom right box, instead of having to go through the algebra, we can just go row total. So the total of the row that contains this box would be 17. The row total, 17. Times the column total of this box. Column total would be 36. And then divide by total, the grand total, which is the 50. 17 times 36 over 50. $12.24. Okay, and that's how you fill in the other two boxes also. So I'm not going to do that because we're going to do another example where we do everything all the way through. Let's do an example all the way through. Example 1. The accompanying table is a study to determine whether ear choice is associated with auditory or language brain hemispheric dominance. What does that even mean? So brain hemispheric dominance is really just saying which side of your brain is more dominant. In other words, are you right-handed or left-handed? And what we're talking about here is, can you conclude that handedness is not independent of cell phone ear preferences? In other words, if you're right-handed, do you prefer to put your phone to your right ear or your left ear? Or do you have no preference? This original table is our observed counts. And then we need to find the expected counts. So before we find the expected counts, I'm going to need my row totals and my column totals. So row total, the first row, 210 plus 103 plus 30. Okay, first row is 343. Second row, 77, 64, 16. 77 plus 64 plus 16. 157. And then I need my column totals. First column, 210, 77. 210 plus 77. 287. Second column, 103, 64. It's 167. Third column, 33 or 30 plus 16. I don't need a calculator there. That's 46. And then I need my total. So total means add up everybody in the sample, which is the original numbers. Or you can also get it by adding just the row total. So 343 plus 157 is 500. You can also get the grand total by adding the column totals. So that's just to check my answer. Let's add up the column totals. So 287, 167, 46. Also 500. So we're good. Okay, and now I need to recreate this table. So I have a right ear, left ear, no preference. I'm just going to write right. Right, left, no preference. And then I have right-handed, left-handed, which I'm also going to write just right and left. And now we have to fill in the expected table. And to fill in the expected table, we're going to be using the formula that we found on the front page. This one down here. So to find the expected, row total times column total over grand total. So let me actually put a box around this. Because that's probably the most important thing on that front page. Okay, row total times column total over grand total. This first box is going to be row total, 343, times column total, 287, divided by total, 500. So 343 times 287 divided by 500. So fraction 343 times 287 over 500. And then round this to 3 decimal places, 196.882. Okay, next one. This is going to be row total, 343, times column total, 167, divided by total, 500. That's going to be 343 times 167 over 500. That's 114.562. This box is going to be row total 343 times column total 46 divided by total 500. 343 times 46 over 500. 31.556. Okay, bottom left here, row total 157 times column total 287 divided by total 500. That's going to be 157 times 287 over 500, 90.118. Next up, row total 157, column total 167 divided by total 500. 157 times 167 over 500, 52.438. And then last one, this one's going to be 157 times 46 divided by 500. 157 times 46 over 500. 14.444. And those are our expected numbers. Part A, state the null and alternative hypotheses. Okay, H0 is going to say that these things are independent. So we're talking about handedness and cell phone ear preference. So handedness and I'm just going to write ear preference and ear preference are independent. H1 is going to say that they're not independent. Part B, find a critical value and sketch the rejection region. Draw the picture. And this is a chi-square test. Chi-square tests are always going to be shaded to the right. Let me actually write that down. And the shaded area is our alpha. Our alpha here is 0.05. And your job is to find, this is a chi-square test, so you're actually finding chi-square star. And this is really a chi-square to, or area to chi-square question. Area to chi-square, this is the same formula sheet that we've been using. Area to chi-square for the chi-square situation is going to be Q chi-square left area df. Left area here is this left unshaded part. So 0.05 is the shaded area which is to the right. I want the other side. To find the other side, do a 1 minus. So 1 minus 0.05 is 0.95, I think. Okay, next up, Q chi-square has a degrees of freedom, df. Now this is where it differs also. So the df here has nothing to do with the sample size. The df for a test for independence is going to be number of rows minus 1 times the number of columns minus 1. Okay, let me write that down. Number of rows minus 1 times the number of columns minus 1. And in our case here, number of rows, there's 2 rows. Minus 1 will be 1. Number of columns, 1, 2, 3 columns, minus 1. So that's 3 minus 1. Sorry there. And when I say rows and columns, I just mean the rows and columns of the original numbers. Sorry. Right? We're not counting the labels, and we're not counting the new numbers that we're writing in. So just the original numbers, which are, there's 2 rows and there's 3 columns. So 2 rows, 2 minus 1. 3 columns, 3 minus 1. 2 minus 1 is 1. 3 minus 1 is 2. So this is really just 1 times 2, which is 2. So we're doing cube chi-square 0.95 comma 2. $5.991. And that's a chi-square star. All right, based on our picture, we did expect a positive answer. We got a positive answer. If for some reason you got a negative answer, chances are if you just remove the negative, it's probably right. What probably happened was you forgot to do a 1 minus on alpha. Part C, find a test statistic. So this is where we have to enter the data into Google Sheets and then use the formula for the test statistic. So let me switch over now to Google Sheets. Here we are in Google Sheets. I'm going to type in the observed numbers and the expected numbers. And I'm going to type them in as columns. So it doesn't matter what order you type them in. You just have to make sure that you use the same order for both the observed and the expected. I'm going to go row by row, left to right. So I'm going to go 210, 103, 30, and then 77, 64, 16. So my observed are 210, 103, 30. That's the first row. Second row, 77, 64, 16. And then the same thing for the expected. My expected, the first row is 196.882, 114.562, 31.556. Second row, 90.118, 52.438, and 14.444. And then from here, it's exactly like the goodness of fit test. So we need a third column where we set up the formula, which is this one. Right? We want to set up this formula. So observed minus expected squared divided by expected, and then add up that entire column. So let me write that up here. Parentheses observed O minus expected E squared. That's the up caret symbol above your 6, 2, divided by E. Let me set up the first box here. To get Google Sheets to do any calculations for you, you have to start off with an equals. So equals, parentheses, O, observed, click on the observed, which is the 210, minus expected, click on the expected, which is this 196.882, close parentheses, square it, which is the up caret 2, divided by expected, click on the 196.882. Hit enter, and then the autofill is correct, so you can use the autofill, or if you don't want to use the autofill, or the autofill doesn't show up for you, just click on the first box, move your cursor to the bottom right until you see a plus sign, and then click and drag it. That should fill up that column for you, and then all you need to do now is add up that column. To add up the column, it's equals sum, S-U-M, parentheses, and then highlight that column. 6.744. So let's go back to the problem. Back to the problem. The test statistic that we just found was 6.744. Part D, find a p-value. So draw our picture. It should be the same picture that we drew in part B. It's going to be shaded to the right. Put your test statistic that you just found on the picture, so 6.744. And your job is to find the shaded area. That's the p-value. This is really a chi-square to area problem. Chi-square to area Chi-square to area for the chi-square situation is going to be a p chi-square df. Okay, p chi-square was 6.744. Comma df, so same df that we used in part B is the number of rows minus 1 times the number of columns minus 1, which we found was 2. We're going to do p chi-square 6.744 comma 2. .966. And we know that can't be right because we expect pretty small numbers for p-values. And this is because p chi-square spits out the left area. But that's not what we're looking for here, right? We're looking for the area to the right. So to find the area to the right, 1 minus. One minus 0.966, 0.034. And that's our p-value. Part E, reject or don't reject H0. Take your p-value and see if it's less than the alpha. Our p-value was 0.034. Our alpha was 0.05. Okay, and if you need to add zeros to make the number of decimal places match, the p-value has 3 decimal places. Let me add a 0 to the alpha. This is really 34 versus 50. Yes, it is less. So if it's less, then you reject. And then finally, our sentence. At alpha equals, state your significance level, 0.05. There is or is not enough evidence. Because we did reject, there is enough evidence to conclude that, what are we trying to conclude? Can you conclude that handedness is not independent of cell phone ear preference? So handedness is not independent of cell phone ear preference. In other words, handedness and ear preference are somehow related. So if you're right-handed, you do prefer one side or the other. And I think I'm right-handed. I think I prefer the right side. Okay, so that's an example of a test for independence. Have a great day, and I will talk to you later.